Hello friends, welcome to my channel. In this video we are going to discuss about the Basel problem. The Basel problem is about the infinite sequence summation, which is 1 plus 1 upon 2 square plus 1 upon 3 square, and this goes up to infinity. This sequence goes up to infinity and this summation is equal to pi square over 6. This was proposed around 16th century, was proved in 17th century by the one of the greatest mathematician Euler. Euler was the first to solve this problem. So we are going to discuss its proof here. Its proof starts with the Maclaurin series. Actually, one of the applications of Maclaurin series, actually sin x is equal to x minus x cube over 3 factorial plus x raised to the power 5 over 5 factorial and so on, and this sequence also goes up to infinity. This sequence can be obtained from Maclaurin series. Actually this sequence is or this equation is a polynomial. Why? Because all the powers of x are integers, and so I can call it a polynomial, although this has infinite number of terms. Now we all know from this equation we can easily find out its roots, because this sequence is equals to sin x and all the roots of sin x will also be the roots of this equation, and clearly the roots of sin x is n pi, where n belongs to integer. So what I mean to say is minus 3 pi, minus 2 pi, minus pi, 0 pi, 2 pi, and this sequence goes to infinity and this here goes to minus infinity. Okay, so this polynomial has infinite number of roots. Now let me consider a polynomial f of x. First of all, let me tell you about quadratic equation. If I have a quadratic equation whose roots are alpha and beta, then I can write the quadratic equation as a into x minus alpha into x minus beta. Okay, and I can get the value of a by comparing it with the original equation. I am going to do the same here to obtain a different equation for the same polynomial. Let me call this polynomial as f of x. Since I know its roots, so I can write f of x as x into 1 minus x over pi into 1 plus x over pi into 1 minus x over 2 pi into 1 plus x over 2 pi, and this goes to infinity. Actually you can see is f of x has 0 as its root, pi as its root, minus pi as its roots, 2 pi as root, minus 2 pi as root, and you can also see that its coefficient a, which I have been talking about in the quadratic equation, is also matching here. The coefficient of by comparing only one term in the whole equation here and whole equation here, I can guarantee to you that both the equations are the same. This is very easy to understand. Actually the coefficient of x here is 1 and the coefficient of x here is also 1, so I can say that the value of a which I would have written here is 1. Now actually coefficient of x is also here 1, can be, you can see that x will coefficient of x will be obtained when this value of x will be multiplied by other other ones present over here in this loops. Let me call this as a loop. Now I have proved that this equation of sin of x by Maclaurin series and this f of x both are the same. So f of x over x is this equation, and by combining these two terms, 1 plus x over pi and 1 minus x over pi, I can write it as 1 minus x square over pi square. By a simple it's a simple formula, x minus a into x minus x plus a is equal to x square minus a square. and writing the whole sequence again like this will give me f of x like this. Also sin of x over x can be written like this over here, you can easily see that. So since f of x is equal to sin of x, so these two equations are also the same. Now equation 1 equation now the equation third and equation 4 are the same, so I can compare its coefficients too. So let me compare the coefficient of x square in both the equations. Okay, so the coefficient of x square over here is minus 1 over 3 factorial, and the coefficient of x square from here can be obtained by multiplying these terms of every loop with one of other loops, that is with this term and with this term 1. Okay, so I can write it like this, that minus of x square over pi square plus x square over 2 pi square plus x square over 3 pi whole square and so on, which goes up to infinity, is equal to minus x square over 3 factorial. Now this is true, so let me put x is equal to 1 in the above equation, that is here. Then I will get, and cutting the minus sign both sides, I will get 1 over pi square plus 1 over 2 pi square and so on up to infinity as 1 over 3 factorial, which is equal to 1 over 6, and taking pi square to the other side will give me this equation 1 plus 1 over 2 square plus 1 over 3 square and so on up to infinity as pi square over 6. So we are done. Actually I forgot you to say that this proof was given by Euler. Euler used this proof for the first time to prove this Basel problem. And that's all. Thank you, and like and subscribe if you like this video.